So this is finally this section is going to get into actually doing significant tests. Today we're going to do most of one. The next lesson, the second part, there's 3 parts to part D, but we'll get to full test in the middle here. This is the homework. Okay, so the conditions are almost exactly the same. In fact, they might look exactly the same, but there's a little difference between one proportion intervals and one proportion test. So we're about to do one proportion test, one prop test. So first one, the same. Random sample, less than 10%, the same. Nothing changed. This one, I don't know if you'll notice the difference, but there's a slight difference. So with proportions, let me try to explain this, maybe. So I'm going to try to explain the difference. So I think this is the way I think of it. I don't know. So with an interval, in the middle of our interval, we have 2 end bounds, but in the middle is called our point estimate. Point estimate in the middle of our interval. And that's p hat, if that makes sense. So that's point hat. So in the middle of our interval is p hat. So we use p hat when we check the large counts condition. We're going to use p hat. That's what we used for one prop interval. For tests, you really are drawing a normal curve here. And in the middle is actually p. So that's the parameter, whereas this is, in the middle is the p hat. So when we do the large count conditions, you actually use, your p hat's going to be over here or something, like it's going to be some value and you're shading that way kind of thing. But p is in the middle. So whatever thing is in the middle, that's what you use for the large count and for a few other things actually. So it's actually helpful just to kind of think that way. So the formula is n times p. It says p naught there or p sub 0. That just means the population parameter. They're making sure you know it's p, not p hat there. I would just put p there. It just makes more sense. That's the population parameter. According to the U.S. Census Bureau, the proportion of high school students who have a part-time job is 25%. Sounds about right. Administrator at a large high school suspects that the proportion of students in the school who have a part-time job is less than the national figure and would like to carry out a test at the 5% significance level. So the null is, I guess we should have asked that, but the null is nothing's unusual. The proportion is 25%. The principal or the administrator says that he thinks it's less than that. So clearly the alternate is going to be p is less than 0.25. Always talking about parameters there, not proportions, not p hats there. Where p is the proportion, the true population proportion of students at the school who have a part-time job. So the administrator takes a random sample of 200 students, finds that 43 of them have a part-time job. Check if the conditions are met for this one. So are the conditions met? Well, so it doesn't say random sample. There was a random sample of 200 students. Check. So you would write that down. Less than 10%. So we sampled 200. This is a large high school, I believe. At a large high school, so 200 is less than 10% of all students at a large high school. That's fair. I'm thinking Collierville's 3,000 or 4,000. And you just say that in words, basically. And then do so I think the hard condition to check is the NP. In this case, it's not p hat, so n times p. So 200 times 0.25 is greater than or equal to 10, and 200 times 0.75 is greater than or equal to 10. So that's I guess the tougher condition, that those are both, so 50 and 150 are both greater than or equal to 10. Be sure to use p, not p hat there. So a standardized test statistic, that's a fancy name for z. If you remember just the generic, it's kind of statistic minus the parameter over the standard deviation. That's the basic idea of it. Oh, there it is. Oh, they put it there. Statistic minus the parameter over the standard error of the statistic. Oftentimes we don't know true things that we many times use at the standard error there. The formula sheet provided, this is why the formula sheet uses the word standard error. We'll be using sample data to estimate the standard deviation. The only exception is in a test about a population proportion where we calculate the standard deviation using the hypothesized value for the proportion, so not the sample proportion. A footnote on the second page of the formula sheet addresses a special case. The formula for standard deviation, p hat, is the formula on the sheet as well. In most cases here, we're going to use sample data to estimate the standard deviation. Okay, so that's good to know. In most cases, that's the case. To form a test, we calculate the test statistic. This is the formula you need. So z equals the statistic, which is p hat, minus the population parameter, divided by the standard deviation, which in this case is square root of pq over n. The pretty example, that was from the other example. We already confirmed the conditions. I explained why the sample results give some evidence for the alternative. So let's just get our calculator out for a second. So 43 divided by 200 is 21.5%. So 21.5% is less than 0.25. So we have some evidence, right? So we're on the right track. So I don't know if it's convincing evidence or not. We got to do some stuff first, but we have some evidence. Calculate the standardized test statistics. So that's where you're going to plug in here. And again, you're plugging in p into the formula there. So 0.21 p hat minus p, so 0.215, which is what we just got, minus 0.25. And then we're using p and q, p and 1 minus p in the formula there. So using the 0.25 number, not the 0.215. We get z is negative 1.143. It's been a while since we've talked about z, just so you know what that means. So if this is the mean, negative 1.143. So that means you're right about there. So that's a z value of negative 1.1 something, right? So it's just a little bit past one standard deviation below the mean. They're saying that's on the formula sheet. You have to kind of piece it together to make this even. Not too bad. Okay, calculate the standardized test statistic and the p-value. Well, we just did the standardized test statistic. But I guess they're saying do norm CDF. Okay, so let's graph this. Oops. Okay, so I'm going to do it. So we put 0.25 in the middle. But there's two ways of doing this. I might show you both. So 43 was 21.5. So someone over here is 0.215. That was our p hat. This is our p. So we want to find out the chance of getting a result that large, that small, or even smaller than that. So you're going to norm CDF this guy. Do we know the standard deviation? So we just figured that out, I think. Let me see what we just did. Oh, we didn't actually figure it out. We didn't type it in the calculator yet. Sorry. Okay, I'm kind of all over the place here, but let's figure out our standard deviation. So square root of control divide. So 0.25 times 0.75 over n, which is 200, I believe. So 0.0306. So standard deviation is 0.0306. So if we did normal CDF, which is honestly this way a bunch of students could do this. So menu 5, 2, I believe. So negative infinity is fine. Upper bound 0.215, I think it was. Mean was 0.25 and 0.0306. So you get 12.6% chance. So the p-value is 0.126. Could we have gotten that with our, I think we had a z-score there. Let's see what the z-score was. It was that. So if you do it with z-score, I think this could work. So we're drawing a normal curve. But this time 0 is there, this is -1. So this was z equals -1.1 something, 143, I believe. And we're shading that way, right? So doing norm CDF with that guy, so that would be menu 652, negative infinity to negative 1, oops, negative 1.143, and we're leaving the default for z values there. We get the same exact, or about the same answer. So there's a little bit of rounding error there, and that's okay. Like we can live with that. So let's see what they did. They did p-values norm CDF. So they used the z-score there. They rounded out the z-score and used that. We got the, I think we got that answer 0.1265. Yeah. And so again, they already did the work for the z-score. We might as well use the z-score, but it works either way, actually. Interpret the p-value. I think this is kind of tough. So the p-value again was 12.65%. So you want to say something like, I like to look at this. Assuming, well, I'll look at mine. So assuming the null is true, that 25% of 25% students at this large high school have a part-time job. Assuming that's true, there is a 12.65% chance of getting a result as a sample as small as 43 out of 200, or even more extreme than that. Let's see what they said here. Assuming that 25% of all students at the school have a part-time job, there's a 12.65% probability or chance of getting a sample proportion of 0.215 or less by chance. And so again, that's the wording they used of getting a sample proportion of 0.215 or less by chance alone. So we want to always see the z-score there, right, along with the p-value. So that is something important. So we did not include the option to use text. So that method I used there of just doing it this way with norm CDF, that is not the best, is what they're saying. We want to see the z-score. We have a way around that where we can do it on the calculator still. But that's interesting. So they do like to see the z-score with the p-value. I'd forgotten that, but that's absolutely true. You can use a TI-83 and so forth. Oh, so they're showing you how to do the test. Well, this is the thing. So let's go back to this one. So get your calculator out. This is fun. Okay, it does the whole thing for you. So this will give you the z-score, I'm pretty sure. Well, let's just see. So menu, I think it's in statistics. Where do you think it would be for a 1 proportion z test? So I'm guessing it's test here. 1 proportion z test. Let's try that. So the null is 0.25. That's what it says, like p naught there, or p sub 0. It should be a sub 0 there, and that's what that is. Number of successes, I think it was 43, wasn't it? 43, yeah, 43 was out of 200. So 43, they gave us that out of 200. So that's basically p hat there. And then you choose which direction it is. So They did less than here, so I'm choosing the less than option, which was the third choice down there, because our alternate is less than. So you have to do that right. If you don't do the alternate right, it's not going to work out. So the z-score should be negative 1.143. It was. The p-value is 0.1265. P has 0.215. So it does give you the z. So if you use this method, you need to write down z. Some of you will show work and show z that way, but you actually could, on the actual exam, just show z and the p-value, and that counts full credit for this. Good. Those are the 4 tests. We haven't really gotten to conclusion yet, but we just went all the way to p-value. So we will make a conclusion. If you have, if you're in class today, I may have provided you with a sheet like this for the example we just did. And so you can see we went all the way through norm CDF there and then do it on the calculator. We did not conclude, but we could. Because our p-value of, what was our p-value? I think I remember, but I just want to make sure. Because our p-value of 12.65%, so because our p-value of 12.65% is greater than the alpha level of 5%, I'm assuming, I didn't read it, but I'm assuming it's 5%. If it was different, we should change that. Let's see, so it's larger, right? Our p-value is larger than our alpha. So we do not reject. We do not have enough evidence. We fail to reject. There is not convincing evidence that the true proportion of students at a large high school who have a job is less than 25% at this large high school or something like that. So you just talk about the context of the problem there. If you want to try a couple more examples, it might help you. So eggs come in different sizes, medium, large, extra large, etc. To meet customer demands, a commercial egg producer needs to more than 87% of its eggs to be classified as large. The producer needs to perform a test at the 5% significance level that P is 0.87. The alternate is it's more than that. The proportion of all eggs are large. In a simple random sample of 60 eggs, 45 are determined to be large eggs. Okay. Check if the conditions for performing this test are met. So random sample, I'm hoping it says something like that. Simple random sample, it does say SRS of 60, so that's, we got it, check. Less than 10%, so 60 eggs is less than 10% of all the eggs produced at this factory that day or something like that. It's hard, it's not, a little unclear what that is. Now, the tough part might be the last one here. So let's see, let me put this some space here. So, so we do n times p is greater than or equal to 10. So n is 60 times p is 0.87. And that should be greater than or equal to 10. And then 60 times 0.13 hopefully should be greater than or equal to 10. You might have typed that when you calculate. I'm a little concerned about 60 times 0.13. 60 times 0.13 is, doesn't pass. That one's too small. 7.8 is not big enough. The other one's big enough, but not that one. So it's not going to pass the test. So if they said, large condition is not met. 7.8 is not bigger than 10. Does a majority of U.S. voters want to get rid of the penny? I do. To find out a test at the alpha level, the relevant hypothesis, P is 0.5. So they're just saying, hey, maybe half the people are in favor of this. P is a portion of all U.S. voters who want to get rid of the penny. In a simple random sample of 1271, 53.5% believe that the U.S. should stop producing new pennies. Assume the conditions for performing the test are met. So we have to check the conditions. I like that. Explain why the result gives you some evidence. So we have to type in, I guess 53.5, which is more than 50%. So that's some evidence in favor of the alternate. Sure. Calculate the standardized test statistic. So to do that, it takes a bit here, right? It's that Z equals the 0.535 minus the parameter, which was 0.5, over the square root of 0.5 times 1 minus 0.5 over n, which was 1271, I think. Type that in your calculator. Let's see what you get. You get Z equals 2.496, I think. Let's just double check I did that right. I think I did set it up right to 2.496. So then you get your calculator out, menu 652. 2.496 is that little area above, so you do go 2.496 to infinity. I'm just going to put 999 because I'm lazy. Keep the default 0 and 1, that's fine because we're using a z-score. Should be 0.00628, 0.0063, perfect. So that is that, and then interpret the p-value. So assuming that the null is true, that 50% of folks really do want to get rid of the penny, the chance of getting a result of 53.5% or greater is very small, way less than 5%, 0.0063. But the chance of that happening is 0.0063. Let's see what it says. There's a 0.0063 probability of getting a sample portion of that or more by chance, assuming that 50% of the population wants to get rid of it. That's your lesson for today.